This video focuses on the use of a Mathematica notebook introduced in the video prior to this to plot the geodesics followed by a massive free particle in the equatorial plane of a Kerr black hole. It uses fewer approximations than the previous video. This is part 3 in the series. Now, this notebook, Mathematica notebook, can be found at this link and numerous other places on the web. This notebook accompanied a textbook by James Hartle. His book titled Gravity and Introduction to Einstein's General Relativity. It's a great book, and this Mathematica notebook and some others came with it. Let me just give you a look at it. Just briefly to make a start. All right, it was written for the Schwarzschild geometry, for the Schwarzschild geometry. And I've talked about it previously in prior videos. What I've done here is modify it to deal with the Kerr geometry. And then actually, since making this video, this is a correction to the previous video under this title. I've put the Kerr version that I've modified into a section on this channel where you can find the files. If you click on the link at the top of the beginning of the channel under the image, there's a link and it'll take you to a Google Drive and you can access the notebook for the Kerr geometry. But I've left for this video, I've left the one in the Schwarzschild heading, but the modification will see out for the Kerr geometry. Okay, now I've put in here the choice. You can change the units from, I've set them all here to 1, except for the dimensional spin parameter. And the mass of the object orbiting the black hole, we'll set that to 1, 2. So when we talk about angular momentum in this video, we're talking about it in terms of angular momentum per unit of mass. Now, so here's the notebook here. Here's the effective potential, discussed that in previous videos. And here our angular momentum, this many units per unit of mass. Okay, here's the energy of the orbit, total energy, bound orbit with minus there. Plotting the two together, the effective potential and the energy of the orbit. And this will give us a bound orbit. In fact, I've chosen particular values that provide a circle. And let me just show you, take all that through. It starts at 25 units or 25 GM on C squared units. And since we're working in units of m equals 1, this just becomes 25. Pick one orbit, and I've chosen very specific values for L and for the angular momentum and the energy here to provide us with a circle, just to show that it's possible with this software, with this notebook, sorry. And here we go here. The blue circle here, the blue circle represents the outer event horizon, which is underneath below the stationary limit surface. The stationary limit surface is at 2 units. And so here we get a circle. And what I'm going to do, every time we evaluate this notebook, it takes a couple of minutes. So what I'm going to do is just to show you how stable that circle is, that circular orbit is. That was n equals 1 orbit. I'm going to change this now to n equals 3 orbits, and then we'll come back at the end of the video and have a look at the end result, just to show you how stable the circular orbit is. All right, so what I'll do now is let's carry on with the rest of the video. So we've got a laboratory containing observer. It's freely falling in the equatorial plane of a Kerr black hole. So here's our laboratory, our particle, object of mass m, massive particle of mass small m, and here's our source mass, rotating Kerr black hole of capital M. So its mass is capital M, and this is small m. It's going to travel along a geodesic in the equatorial plane here, and we want to be able to plot that geodesic. Use numerical integration. It's not possible to find an analytic exact solution, so we have to resort to numerical integration techniques, which is what we're going to do. But before we do that, we need to come up with a form of the integrand. Now, in the last video, I made 3 approximations, and in this video, I can improve on that by making only 1 approximation and producing a better result. Now, in this freely falling frame, the laws of special relativity apply as long as the region of space-time around it is kept sufficiently small. So for a sufficiently small region of space-time around the laboratory, including the laboratory, the laws of special relativity apply. There are two conserved quantities here. The energy, that's the total energy of the laboratory or the particle or the observer in their orbit, and the phi component of the angular momentum is conserved. That's the angular momentum around the rotation axis. Okay. The total angular momentum is not conserved because that also involves the polar angle here. Okay, so the total angular momentum is not conserved, but this component of angular momentum, this contravariant component here, is conserved, and so is the covariant component. Let's have a look now. So, the reason they're conserved is there's two Killing vectors in this geometry, one in the time direction and one in the phi angular direction. So let's deal with the phi angular direction first. So we have some Killing vector k there, has components k phi basis vector e phi times basis vector e phi, and k phi set to 1. Okay, so here's our Killing vector in the phi direction, and we know that there is the form momentum along in the direction of the Killing vector is conserved or produces a conserved quantity if we take the dot product or the inner product, scalar product of the Killing vector with the form momentum, and we're going to show that the total derivative with respect to proper time tau is 0. Okay, so what we do here is k dot p is the form momentum of the laboratory, is dt tau, g phi phi, k phi, p phi, because it's only the phi component involved. These are all 0 up here, so that part of the form momentum drops out. And so in the direction of this Killing vector, we have this conserved quantity. Now k phi is 1, so that drops out, and we have g phi phi times p phi. Well, the metric term lowers, the metric component lowers this element here, lowers this index here. We get the covariant form of the form momentum in the phi direction, and dt tau of that is 0, so that implies that p covariant phi is equal to some constant h. This is our angular momentum in the phi direction. Now let's look in the time direction. A Killing vector in that direction, kt et, is we're going to set that to et equals c. On this channel I scale things in terms of ct for the biolinguist coordinates, so I use ct instead of t. So you'll have that factor of c there instead of 1. Okay, again, the total derivative with respect to proper time tau, k dot the form momentum, that's the Killing vector in the direction of form momentum, k dot p, is dd tau, gtt, kt, pt. And what we have is dd tau, gtt, c, constant c, which we can pull out front there. This metric component here lowers this index here, and we're left with the covariant form of the momentum in the time direction times the constant c, which gives us the energy. Okay, we know the derivative of that is 0, so c times pt, covariant t, is constant, and that's equal to the energy. The minus here because the metric signature I use on this channel requires this to be a minus in order, because all this part here is also negative. Now, earlier in this series of videos, expressions were found for both of these quantities. We found the covariant form of the momentum around the rotation axis, so in the phi direction, p covariant index phi is this object equal to h, and for the energy term we found this. That was all the subject of previous videos. What we want to do is to get phi dot by itself, that is d phi d tau. So we seek an equation in the form phi of r because we want to plot the geodesic that this laboratory follows in the equatorial plane. So we seek an equation in the form phi as a function of r to describe the motion of the laboratory in the equatorial plane of the rotating source, mass m, capital M, and we begin by finding phi dot. Now we have two equations to help us locate phi dot, determine its form, okay, and this is the equation we're going to use, but we're going to use this energy equation here to get rid of this ct dot term over here by rearranging this equation to get ct dot by itself, and then we'll substitute it into here, okay, to determine the momentum, so angular momentum in the phi direction. So let's have a look at that. So from the second equation, the energy one, we have this. and taking this second term on the left here over to the right, we get this object here, and then multiplying through by 2 on m and multiplying through by the inverse metric component, GTT, index raised, we get minus 2 on m GTT E on C minus GTT GT phi dot. Okay, and that m on 2 cancel because we multiplied by 2 on m. And what we end up with then, we then substitute that into the p covariant index phi. That gives us this times this plus this n bit term. Okay, so we've eliminated CT dot and we've got a phi dot here and a phi dot here, so we're on our way, we're making progress. Let's expand that out. G phi t times this negative times this. Now GTT upper indices is negative, G phi t lower indices is also negative, times a negative, so we end up altogether this being negative, so we just have to be careful about the signs here as well. Again, multiplying through, we end up with all this. Just bear in mind there'll be some changes here. G phi t and G t phi are both the same metric term because of the symmetry, and so that's just, we end up down here with them being squared and positive because they're both negative and multiplied together is a positive. Then we have GTT and minus m on 2, that's negative, so that'll produce a positive over here. G upper indices TT, that's the inverse metric term for the time component, is this object here. Delta I've explained in plenty of other previous videos, so I won't repeat it here. And when we substitute in the metric terms, we end up with this. We'll just leave this one to the end just to keep the expression as tidy as possible. We'll deal with that towards the end. We don't need to deal with it now. Remember, ultimately, we're trying to get phi dot by itself. That's d phi d tau, the derivative of phi with respect to proper time, tau by itself. Next line over. Okay, so expanding that out, and with the delta term there, we had 1 over delta, which if we common denominator and then flip it upside down, we get this, because it's 1 over delta, times GTT, upper indices. Sorry, this is the whole of GTT, my fault, sorry, the whole of GTT upper indices, times this bit here, times E on C, plus this bit, okay. Next line down, what we're going to do is we're going to get a common denominator for this part of the expression in here, this term within this first term, and we'll get a common denominator here, and we'll make that common denominator c squared r. Okay, so that means we're going to have here c squared r cubed, c squared a squared r, which we have here, that times the E over c. And then down here in the second term, this expression, we will have same thing again, common denominator c squared r. That makes this up here c squared r cubed, c squared a squared r plus that. Okay, on the here we have 2gm ac all squared. There we have this c4 r squared term down here because remember it's squared there. And what we're then going to, so we multiply that through. Okay, so we have this denominator here, this numerator. And what we'll do is this c squared here should cancel with the c squared there. Okay, and then we will multiply this numerator by this over this denominator, and this c squared r is going to get pulled out under the E. Do that. And here, this numerator here, multiplied by this over this denominator. Okay, that'll give us this m on 2 times that times this. Okay, so here's the only approximation we're going to make in this video, the only approximation. In the last video prior to this, I made 3 approximations. Okay, I set E on R to 0. I said it's approximately, E is quite small relative to R, and so we'll set that to 0. That term will drop off. And then I made one other approximation further on. I'm not going to do that. The only approximation in this video will be to say, look, the order of this numerator is R cubed. The term of highest order is R cubed. And the order of the denominator, the numerator up here, the highest order is R cubed, is 3, is a cubic. Same down the bottom here. we're going to make the approximated. This is approximately 1. And if you plot this, you'll see that it is actually, and set all these units C, M, G to 0, and just keep R and A in this case being the dimensional spin parameter because you've set G, M, and C to 0, capital M that is. And if you do that and plot it, you'll find that after the event horizon very rapidly approaches 1 and remains 1 for as far as you can go. So 1 is a good approximation. Down here, the second term, same thing here. 1 is a good approximation. Plot that as well. Set all these units G, M, and C to 1. Plot all and just keep A. Set them all to 1 except for A and R. Plot those with respect to R. And for anything beyond the event horizon and the stationary limit surface, pretty well is 1 all the way across. It's just a flat line when you plot it. Okay, so that's a reasonable approximation. Okay, and if we do that, if we set that to 1 and that to 1, we end up with minus 2gm on c squared times E on R. So gone. This one gone, and we're left with m on 2gm all squared times phi dot c squared over c squared R squared, and then just this n term here, which we'll deal with shortly. All right, next bit. So let's bring all that forward to the next page. And we know that that's the an approximation, a good approximation for the phi component of the angular momentum, the covariant component of phi for the angular momentum. So it's approximately the h. Okay, so what we're going to do is take this first term over to the other side. We'll do that. And then put those in parentheses and multiply through by 2 on m, cancel those out. And this is an error I made in the last video and I needed to correct it. I pointed out in the last video, but I'm not happy with it. I'm going to correct it and change it. So I'm remaking the whole video. Okay, and we're left with, okay, on the left-hand side when we do that, we get this. Okay, so why not make a common denominator here too? So c squared R squared is our common denominator here. All right, I'm not going to evaluate G phi phi just yet. Okay, and when I do that, on the right here, multiply by 2 on m and get a common denominator. So the common denominator will be c squared R. So I'll have h c squared R plus 2gm E on c squared R. Then we've got to multiply through by 2. So we get a 2 out front, and 2 by 2 gives us 4 here. And also the m underneath. And also there was another error. I had an m, a small m up here next to the big M. So another reason for remaking the video. Okay, multiply through by the reciprocal of this leading coefficient, and we get phi dot by itself. Over here we get this. Multiply through, well, the c squareds can go. This r can go with one of these up top, and we're left with just r multiplied by this for the numerator. So we get 2h c squared r squared plus 4g m, capital M, e r. And then underneath, we're going to have that r and that c squared are gone. We're going to have m times all of this. So we have m times the denominator. Okay, that gives us phi dot, d phi d dot. So we're making progress. Next bit. Now what we want is we want d phi du, and the way we get d phi du is d phi dr, the chain rule, times dr du. Okay, now we make the substitution too. That r is, I'll put a couple of things here together, I rushed a little bit, but r is 1 on u, dr du is minus 1 on u squared. We're going to make a substitution, and when we integrate numerically, we'll work in terms of u instead of 1 on r. Okay, so d phi du is this, so we end up plus or minus this dr du, this business here, and here's our integrand from before, because remember it was d phi d tau times dr d tau, which was d phi d tau times d tau dr. D tau dr was this bit on the end. That's all in the previous video. I'm not going into that here, but we put in here where the r squared was, put on 1 on u squared, and here 1 on u. Okay, we get this now. One more thing we can do is up here, if we change this to u on u squared, okay, so u on u squared, then it's this common factor of 1 on u squared we can pull out front. So we take that out here, and this becomes 2hc squared plus 2gmeu. Remember that was u over u squared. So there's a u there. And then we have this 1 on u squared times 1 on u squared. So let's multiply one of them through. We'll get a 1 on u squared here, and we'll get a u squared here, and a u squared times c squared on u squared. So that'll cancel. Then the next one will multiply through. We'll have a u to the 4 here, and we will have a u squared here, which we then multiply throughout to give us a squared u squared. U squared times 1 on u squared is just 1, and then u squared times all this with a u on the end gives us u cubed. And so this is our final integrand. This will be the integrand we use for the numerical integration. All right, that's what we're aiming at. And okay, also from previous videos, here's our effective potential, where E is this object here, half mc squared epsilon squared minus 1, which has been covered in previous videos, but that's our effective potential. You'll see that in the notebook. I think I've already shown it to you already. And here's our integrand. Here it is. We're going to numerically integrate this and then make a parametric plot of it, so the x and y components of it. Right, now for a few examples of these plots. Okay, an example of a bound orbit. H equals plus 4.65 units of angular momentum per unit of mass. E is minus this. Starting distance 40 gm on c squared, or just 40 units on this plot. One orbit. So n equals orbit, which is the number of orbits. So this is one orbit, and this is one orbit here. Here we go, like that. That's the effective potential. Okay. The orange line is the energy. It's set at minus 0.01, and the blue line is the effective potential. Next bit, n equals 2. 2 complete orbits. You can start to see more complicated behavior. I'm beginning a precession here, you can see. It is visible in the first one, but I won't go into there. Let's go to n equals 3. 3 orbits, and you can see very clearly how the orbit is precessing. Big loops here indicate how it's precessing. All right. And at the video, I showed you this one, and showing that circles are also possible. And I set for this one n equals 1 orbit. What I'm going to do now is show you what n equals 3 orbits look like, because while we've been talking about this video, the notebook has been plotting n equals 3 orbits. Okay, so I set it running earlier. If you remember, there's your effective potential here and the energy. And n equals 3 orbits. I showed you at the beginning of the video n equals 1 at the very start. And some other parameters which I've talked about in previous videos. Okay, here's our integrand here. The integration variable w is going to be integrated between u1 and u2, or u1 up to u. And we're working in spheroidal coordinates, remember? So we have, this is r squared. So in u it becomes 1 on u squared plus the a squared and cos of the angle and sine of the angle for the y component. The x component is this, and then we plot the x and y components together as a pair. And what we end up with, just to show you 3 orbits, including blue disk representing the Kerr black hole. Its event horizon is less than 2 units, so it's underneath. The actual stationary limit surface is at r equals 2 right there, and this blue line is just accentuating the fact that here's the event horizon, the blue line. So here's 3 orbits, so it's quite stable. It can have multiple orbits. I could put more in there, 6, 7, whatever. I just want to show that circular orbits are possible and stable ones at that. In future videos, we'll look at that. All right, and that's it, finished.